Hello students, in this particular series, we are talking about transformation geometry. If you have not seen the other videos of this series, check the link in the description. It contains all of them. Transformation geometry is very useful if you are trying to solve Olympiad level problems, as well as problems for ISI and CMI entrances. But more importantly, they are very beautiful. In this particular video, I will talk about one area of geometry which is often overlooked in the initial stages of Euclidean geometry. This is called projective geometry. So instead of telling you complicated formulas, I'll actually talk about art today, and I will ask you to draw a three-dimensional figure in a scientific manner. So the story goes like this, that during the Renaissance in Europe, artists and architects learned how to manipulate or create illusions of three dimension on a piece of paper. So suppose you wanted to draw a few bricks. So before the Renaissance, before this mathematical idea of perspectivity or the point at infinity came into being, bricks were drawn like this on the piece of paper. If you wanted to draw bricks, you would draw something like this. And if you wanted to draw humans standing on some part of that particular floor, you would draw like that. And of course, it doesn't look three-dimensional, but it conveys the idea. Even in Mughal arts, you can Google that. In Mughal period in India, artists were drawing pictures like this, which looked two-dimensional, but which wanted to depict something three-dimensional. In Europe, however, they discovered something very interesting. They discovered how we can create the illusion of three dimension on a piece of paper. And this is used until today, even in softwares like AutoCAD, when they are drawing pictures. So let's see how we can do that, and what is the relationship of it with geometry that we do for Olympiads and so on. So suppose you wanted to draw a few bricks on the floor. How would you do that? Well, the first thing you have to do is that you have to fix a point at infinity. But that's just any point P on the plain piece of paper. Nothing special about this point. Now what you do is, you draw a line, which is like this, which is the starting point of your floor. And then you place equidistant points on that line. So for just the sake of it, I put 7 points. What I'm going to do is, I will draw these points, a line from these points, each of these points, to the point at infinity. So like this, I'm going to draw it. And so far it's so good, we do not really understand what's going on, why this might do any good to us. But we will soon see what's happening. Okay, so here we go. The second step is to actually create the first set of tilings on the floor, the first set of bricks. So I'm just going to draw a line like this. And I got the first set of bricks. These are the first set of bricks. or the first set of tilings on the floor. And now the real interesting part begins. I need to draw the second set of tiles, but I also need to create an illusion to my eyes so that the size of the second set of tiles appear equal to the first set of tiles. How do I do that? So basically, I want to draw a line like this somewhere. But I want to do it carefully so that the two tiles on the two rows appear to be equal in sizes. The trick is actually very simple. What you essentially do is you draw a diagonal of one of the tiles. So remember, since there are tiles on the floor, the diagonals actually should be along the same straight line. All the corners of the tiles should be on the same straight line. So you got the second point here, the second level. Now you know how to draw the second line. Here we go, the second line. You also know how to draw the third line. Here it is. And you draw the third line. Oops, sorry. I hope you were able to draw this as well in your notebook, and you were able to see and enjoy the illusion that is being created here. The fourth line is here. Of course, if you measure it in the Euclidean sense, if you just take a scale and measure it, this one is smaller than this and smaller than this and so on and so forth. But they appear to be of equal sizes in the human eye. Let's do the next one. Here it is. And the next one. Here we go. And so forth. Of course, you can draw more lines. Like so. Just to give this a better infinite feeling. And at last, you can actually delete this point of infinity. And what you are left out is just the illusion of the plane. Illusion of the plane. You see, now if you look at this picture, it looks like tiling on the plane and it looks three-dimensional. The point of infinity, though we drew it at the beginning, is now vanished. Of course, we have erased it. And you can obviously make it come back to the drawing scales by just joining all those lines which are parallel. So comes the very important concept of projective geometry. The parallel lines are a pair of lines which meet at infinity. These two lines on the plane are actually parallel, but in the projective plane, they actually meet at some point in the infinity. In projective plane, every pair of straight lines meet at one point. Let me write that. So, in projective plane, every pair of line, each pair of line meet at a point. So there is no pair of line which never meets. Therefore, in that sense, there is no pair of parallel lines in the projective plane. There are various models of the projective plane. The word line and the word point, can have very different meanings. Maybe in some future video, I'll give you one such model of the projective plane where the lines are the planes passing through origin, in R3. So you take the three-dimensional space, you put a coordinate system there, and you take all the planes passing through origin. Those planes are the lines. So you define the planes as the lines. And the points are the lines passing through origin. Through origin. If you think about it, you'll find that this is also a model. This is actually a model of the projective plane. It satisfies that condition that any two lines pass through a point. Because lines are planes, so any two planes pass through a line, but line is a point. You see what I'm saying, right? The actual Euclidean line is a point in this particular model. I hope you learned something from this video. Projective geometry is fascinating. It is also very useful to solve beautiful Olympiad level problems. If you are interested in mathematics, computer science, physics, the real mathematics, computer science and physics, then you might enjoy the beautiful courses that we have at Cheenta. Check the link in the description for more details and keep on learning great mathematics. Take care and bye.